Let's learn today to use UNet Transformers for image segmentation. First of all, let's demonstrate what is the final result so we can see what we are going to do in this tutorial. On the left side you can see an original image, and this is the ground truth. This is from the dataset. You can see this is the hair segmentation, and this is the final result. This is the prediction of the hair using our model, the one that we are going to train in this tutorial. So let's jump to more images. Let's for example see this one. As you can see, once again, this is an original image from the dataset. As you can see, this is the mask. The mask is always white and all the rest is black, and this is the predicted mask. As you can see, a very good result, and as you can see more and more, this will be our tutorial, and it will be based on a UNet transformer. So the tutorial will be based on this dataset. As you can see here, this is the dataset card. It is a dataset under the Hugging Face, and you can see here all the images and its mask. Basically, if you go here to the files, you can see that the dataset is a Parquet file. So we will learn how to convert this Parquet file to a regular images and masks. And if we go back to our code, we will divide the process to 3 steps. The first step will be extracting the Parquet files into images and masks. So this will be the first process. The second process will be building our model. As you can see, this is the code. And finally, we will save the best model, the best model weights. We will save it in one of our local folders. And the last step will be testing our model. And testing our model will be running. We can run it and you can see the result. Basically, it will be running through all the test images and displaying the predicted mask one by one. And as you can see right now, displaying one by one and then storing the tests, masks and images in a new folder. So this is going to be our tutorial. We will start as always with the installation part. So let's start with the installation. As always, I will leave a link for the installation txt. This is the file. There is also here a link for the dataset. We will deal with this later. But as for starting the process, we will create a new and fresh Conda environment. Let's name it UnetR, and it will be based on Python 3.11. After creating the environment, of course, you have to activate it so you can use it for installing more packages. So what we are going to do next, we have to install these 4 packages: pandas, py-arrow, pillow for images, and tqdm for the progress bar. After that, we have to install a TensorFlow. And now this is important. If you are using a Windows environment, you can only use the CPU version. So you can run the simple pip install TensorFlow and choose this version. Our tutorial will be based on the 2.17.1. If you have a Linux environment and also a GPU card, you have to write this command: pip install TensorFlow and CUDA, and this will install all the relevant add-ons of TensorFlow in order to run the process using the GPU card. And after that, you have to install these 3 Python packages: the OpenCV, sklearn, and Patchify. This is for patches in the transformers. So I will not run these commands. I already done it on my local machine. I will use the simple one, the CPU. Of course, you can run it on a GPU card. let's continue to deal with dataset. The next step will be dealing with our dataset and downloading and prepare it for our training. So this is the link. As you can see, it's a dataset on Hugging Face. Let's go to the website. As you can see here, it's named Figaro Hair Segmentation 1000. And if we look here, you can see that for each of the images, there is a mask that white marks the hair, and all the rest is on black color, which is anything that is not a hair. You can see here in this image as well, the hair is white, and all the rest, the face, the body, all the rest of the image is black. And of course I can scroll here, and as you can see, all the images are in the same concept, hair in white and all the rest in black. But when we are going to download, when you would like to download the data and we go to the files and versions, you can see here there is a data subfolder, and inside this data there are two Parquet files. One is the trained data and the second one is the validation data. So basically what we have to do is download these two files. As you can see here, there is a button for download, and after that write a code that convert or let's say extract the images and the masks out of this Parquet file. So I already download these two files. You can see these files here. I store it on my D drive, dataset segmentation, Figaro Hair Segmentation. You can see here these two Parquet files. So now let's go for the code. The first code named step 1, convert Parquet to images. And as you can see here, this is the code for reading the trained Parquet file and convert it to images and for masks. We are creating a new subfolder named images and masks, and also we are running a loop using for each of those Parquet files, and then store and save the images. You can see here we are storing the image, and here we are storing the labels, the masks. So and here this is when we are loading the train Parquet file, and here is the test or validation Parquet file, and everything will be stored in the same folder under train and test. So let's run the code and see the result. We have 1000 images and in the train dataset, and it starts extracting the information from those images and save it on our destination folder. So the process has finished. As you can see, we have 1000 trained images and its labels, of course, and 50 test images that are stored in the same location. Let's look at the folder, and now as you can see we have train and test. Let's open the train folder, and inside it you can see images and masks. Let's open the images. As you can see, each of the images are images of a face, and if we go, let's for example open the first image, and this is the image. Okay, let's leave it here, and now let's look for the mask image of the first one. Let's open it as well. Let's put one next to each other, and now as you can see, the white mask indicates the hair in this person. So mainly this is the same concept in all images, and now we are ready with our dataset. Now we are ready to build our model for do segmentation for the hair in images. So we finished prepare the dataset, and let's move to the next step. And the next step will be building our model, our UnetR model, and do all the training stuff. So I will leave another code named step number 2, train UnetR model. So as you can see, this is the code. I will do a brief description of the relevant part in the code. We'll not do a freestyle coding. We just cover the code and run it and see the result. So what we are going to do here, we will prepare the TensorFlow pipeline. We configure and build a UnetR model using a custom implementation. We will compile and train the model with the appropriate callback and checkpoints, learning rate reduction, login and early stopping. And basically we will demonstrate how to apply a vision transformer based architecture like a UnetR for this hair segmentation. So let's start. The first part is the importing the relevant Python packages. We will import the necessary libraries for file handling, image processing, patching, and deep learning. But watch here, we will import these two parts, one from a class, from a Python named UNet_2D, and this is the structure of our model. I will cover it later. And also we will use another Python code, the Python file named metrics, and we will use the function dice loss. I will explain it later. Next, we are setting up the UnetR model configuration parameters. As you can see, the image size will be 256. It's a color image with 3 channels, and also the number of layer and the pet size. I will not cover the process, the theoretical process of transformers, so I'm just jumping directly to the practical side. So in this process we are make the necessary configuration for our model. Next, we will create a utility function, this one to create a directory if it doesn't exist. We will use this function several times in this code. Next, load dataset. This function loads and split the dataset into training, validation, and test dataset, and return the information back with the train X are the images, train Y are the train masks, and also validation is X are the images, the validation images, and etc. 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 Next function, read image, as you can see here, this one. And in this image, we will read and resize an image, and this convert it into a non-overlapping patches. As you can see here, we are using OpenCV function to read, to resize it to 256 by 256. Then we normalize the data between 0 and 1 by dividing it to 255, and then we are creating the patches of the loaded image. Let's move to the next function, read mask, and this function process a grayscale mask, resize it, normalize it, and add the dimension, a channel dimension. So this deal with our label, with our mask. We are reading the image as a grayscale, resize it to the required dimensions, normalize it so the values will be between 0 and 1, and then we are adding a channel dimension. Next function, and this TensorFlow compatible function wraps our image and mask reader using NumPy function. And next, the TF dataset. This function builds the input data pipeline using TensorFlow dataset API. Now this is the main script, as you can see here, starting from here. First of all, we are setting a random seed, so we will get the same results if you run it several times. Then we are creating a directory, this directory, and this directory to save the train model and all the logs. As you can see, it will be under the temp models unit binary. Next, we are defining the training hyperparameters. Batch size will be 8. We will load 8 images for a batch. We will run it for 500 epochs. Our learning rate will be 0.1. And as you can see, the model path will be named as model.keras under this folder. We will also generate a log file named log.csv. Next, we are loading the dataset from the disk and splitting it into train, validation, and test using our previous function named load dataset. And next, we are creating a TensorFlow data pipeline object for training and validation sets. After that, we are building and compiling the UNet model with the dice laws and SGD optimizer. As you can see here, we are creating a model variable and running this function named build UnetR 2D. And this function is part of the code named UNet, this one, UNetR 2D. And this code in charge of building the UnetR architecture model. This script defines the architecture of the 2D UnetR. UnetR is a unit with transformer model in TensorFlow and Keras, aimed at image segmentation task like our hair segmentation. And it's built of several key components and MLP. As you can see here, MLP block, a multi-layer perception used inside transformer encoder blocks with activation and dropout for regulation. There is the transformer encoder that implements a standard transformer block with multi-head self-attention, skip connection, normalization, and MLP. There is the convolution blocks. As you can see here, there is a convolution block and a deconvolution block. This is a classic CNN layer used in the decoder for upsampling and refinement. And this helps bridge the transformer and the CNN component. Next is the patch embedding. The input image is split into non-overlapping patches, then projected into the higher dimensional space before being processed and transformed. And so these are the parts. I will not cover the theoretical part, but it contains all the relevant process of building our UnetR model. But most important, we are going to run this function named build UNet 2D, and this function builds all the components, all the building blocks of this architecture, and it uses all these functions to build the final structure. So let's go back to our code for the train. So here in this model, we will get an empty structure without weights, of course, of our UnetR model. So in the compile process, we are defining a loss function named dice loss. And this dice loss is a function from the code named metrics.py. And this is the code. What is the metrics.py? This script defines custom evaluation metrics for image segmentation tasks, especially designed for binary segmentation problems like we are dealing with hair segmentation. And the main metrics implement is the dice coefficient which measures the overlap between the predicted segmentation mask and the ground truth. It is especially useful when dealing with imbalanced classes, as it focused on similarity between the predicted and the actual mask area. So we are using this function for our process. So let's go back for our train code and let's continue. After that, we will print the structure of our model, and next we will define the callbacks. So what are the callbacks? These defined callbacks are for saving the best model, doing all the logging, and updating the learning rate, doing the learning rate adjustments, and also the early stopping. And we are going to monitor the validation loss, you can see here, and we will reduce the learning rate, and this will be the factor. And also we will do an early stopping. The early stopping will monitor 20 epochs. If there will be no improvement after 20 epochs, we will stop the training and we will save our best model weights. And finally, the Feit function. The Feit function in charge of the training the model on the dataset and the validation and using our callbacks. As you can see, this is the training dataset, and the epochs, we are sending the number of epochs that we decided, 500 epochs. Of course, we are not going to wait 500 epochs. It probably will do an early stopping. This is the validation dataset, and here are the callbacks, the one that were defined here. Let's run the code. So here is the summary of the model, and now it starts training. I'm running it on a fast forward. As you can see, each time there is an improvement and the model is being saved in this location. And after 20 epochs with no improve, it will stop training. So let's jump to the result. The training has finished. Let's see the result. As you can see here under temp models UNet binary, we have model.keras, and this after several hours contains the the weights for our model, for our dataset. We can also see here the log CSV. Inside it we can see all the process and the progress of each of those epochs. But let's continue to the final and interesting step, which is testing our model. So I will add another Python code named test the model. As you can see, this is the Python code. I will cover the code. Basically, it contains several parts: the configuration setup, and the environment setup, and the model loading, the dataset loading, image processing, and ground truth mask preparation, predicting and visualization, and saving and displaying the result. So let's cover each of those parts. First of all, we are importing the relevant Python packages, and after that we are defining the configuration parameters for the UNet model. Basically, they are the same as for the training, because we have to do some transformation for the images before we run the inference. And next we start the main execution block. It starts here. This is the main block. First of all, we will set up a random seed, so we will get the same result. Next, we will define a directory where the prediction result will be saved. We would like to save it on this folder named result. Next to, basically, it will be next to our model weights, and we will create this directory. Next, we are loading the model. As you can see, this is the full path for our model. And here we are also along with the custom dice loss function, the same that we used earlier. After that, we are loading the Figaro Hair Segmentation dataset. We are doing the same process of train, validation, and test. And we will print the size of each of those splitted dataset. Basically, we need only the test, so we are just running this process to extract the test data. We are running a loop on the test images and the test labels, the test mask. So this is basically our ground truth. So we are running a loop through each test image and its corresponding ground truth mask. Then we will read the image. First of all, we are getting the file name, and then we are reading the image and resize it to match the model input dimension. This is where we are normalizing the values of the image, so it will be between 0 and 1. And after that, in this process, we are converting the image into a known overlapping patches to match our UnetR input. Next, we will read the ground truth mask. Here it is. This is the part. Read the mask, resize it to the same sizes, normalize it so the values will be between 0 and 1, and we will add a batch dimension. Next, it's the prediction process. As you can see, we are running the prediction for each of those images, and after that we are basically running this concatenate, and this line takes the predicted mask, which is likely a single channel grayscale image, and replicate it across the 3 channels. So it will basically has the same values for the green, blue, and red. So then we will have the ability to display it as one image along with our original image. After that, we concatenate the original image, the ground truth mask, and the projection for comparison. That means in this process we are generating one image that is composed of these 3 images: the original image, the original mask, and the predicted mask, and then create a save path for this concatenate image and save the image in this folder. After that, we OpenCV expect the input image to have a data type of uinteger8 or flow32, so we convert the float image to this Python type, displayed using OpenCV. And after that, we show the result using OpenCV window and wait 1 millisecond before moving to the next image. So basically we are going to run a loop through all the images and display one after each other. So let's run it and see the result. As you can see, it's running pretty fast. This is the original image, this is the ground truth, and this is the predicted mask. Okay, it's finished. Now it stored those images on the result folder. So let's look for it. As you can see, here it is. And let's open the first image. Let's resize it a little bit. Now, as you can see, this is the original image, this is the original mask, and this is the predicted mask. Very nice. Let's try another one. This is the original image, this is the original mask, and this is the predicted mask. Not a great result, but not bad as well. This seems perfect. This is good as well. This is great result. So Hopefully, I hope you enjoyed this tutorial. As I mentioned earlier, the code will be part of the video description. You are most welcome to subscribe my channel. Bye bye.